In this video, we will learn how to find confidence intervals for population proportions. Before we look at constructing a confidence interval, we need some notation. P hat is the sample proportion. P is the population proportion. E is the margin of error. And Z sub alpha divided by 2 is our critical Z-score. This is the Greek letter alpha. We'll talk more about each of these in the example problem. It would be great if we knew what proportion or what percent of the US population, or even the world population, that has antibodies against the coronavirus and therefore may possibly be immune. Ideally, we would test every person in the United States to determine if they have antibodies to answer this question, but that's unrealistic. So instead, we take a random sample of a subset of the US population. The proportion of people with the COVID-19 antibodies in our sample is called P hat. The proportion of people in the population with COVID-19 antibodies is called P. The population proportion is the value that we are trying to find, and that value is currently unknown. That value will probably always be unknown, because again, it's unrealistic to be able to test every single person in the population. A recent study in New York State found that out of 7,500 people, 14.9% tested positive for coronavirus antibodies. This tells us that the sample proportion P hat is equal to 0.149, 14.9%. In fractional form, we could also write this as about 11/18 out of 7,500. The sample size N is equal to 7,500 because 7,500 people were sampled in total. The sample proportion P hat is the best point estimate for the population proportion P. So P hat will go in the middle of our distribution, and our confidence interval will be based around that value. The most common level of confidence is a 95% confidence level. Our goal is to find the values that go on either end of this confidence interval. Our first step will be to find the Z-score that is associated with these values. Because we know that there is 95% in the center of the distribution, we know that the area on either end of the distribution would be 2.5%. So our critical Z-score is found by looking at our Z table for an area of 2.5%. 2.5% is 0.025 as a decimal, and the associated Z-score would be negative 1.96. So our critical Z would be Z with a 0.025 subscript, and that is equal to negative 1.96. And I'll actually write this as plus or minus 1.96 to show that this could be the Z-score on either side of the distribution. The formula for finding the confidence interval is P hat plus or minus the margin of error, where the margin of error is the distance between P hat and our critical Z. The margin of error can be found by taking the critical Z-score and multiplying it by the square root of P hat times 1 minus P hat, all divided by N, where N is the sample size. So for our example, we have P hat equal to 0.149 plus or minus our critical Z-score of 1.96 times the square root of 0.149 times 1 minus 0.149, all divided by our sample size N, which was 7,500. In the calculator, we can now enter in just the margin of error part of this formula. And for the margin of error, we find 0.00806. And then finally, we will add and subtract. When we do the subtraction part, we have 0.14094, and when we do the addition, we get 0.15706. We were looking to find the value of the population proportion, and that is why we write our answer this way, to show that we expect P the population proportion to be between these two values. We still have not found the actual population proportion of the US with COVID-19 antibodies. We are only 95% confident that the confidence interval we have calculated actually contains the population proportion. Another issue with this is that this study was actually conducted in New York State, so only New York State residents were included in this study. If New York State residents are not representative of all United States residents, then we may have some bias in our values. This does give us a pretty good estimate of what proportion of the United States we might expect to have COVID-19 antibodies. Now let's suppose that we had a p-hat value of 0.149, same as the previous problem, but we decided that we were only going to sample 1,000 people instead of the 7,500. What then happens to the confidence interval? When the value of n increases, this causes the margin of error to become smaller. So ideally, it would be better for us to have a larger sample as opposed to a smaller sample so that we can get more pinpointed results for our confidence interval. If we want our margin of error to be a certain size, then we can solve this margin of error formula for n in order to determine how many people we would need to sample to achieve that margin of error. The margin of error in this example was very small, less than 1%, 0.00806. Let's say we were okay with having a margin of error of 1%. How many people would we need to sample to keep our margin of error at 1%? The margin of error formula is E equals z sub alpha divided by 2, the critical z-score, times the square root of p-hat times 1 minus p-hat, all divided by n. We want the margin of error to stay at 1%. Our critical z-score was 1.96, and our p-hat, or sample proportion, was 0.149. We will leave n in the formula because this is the variable for which we are trying to solve. Using algebra, we can find that n is equal to 0.149 times 1 minus 0.149 divided by the quantity 0.01 divided by 1.96 squared. This is approximately equal to 4871.1. So we would need to have greater than or equal to 4,871.1 U.S. residents. Since we need our population to be greater than or equal to this value, that means we need to round up to 4,872 so that our margin of error will stay within 1% of the true population proportion. You can also find another equivalent formula in the textbook on page 307. This formula introduces the value of q hat, but q hat is just the quantity 1 minus p hat. They're the same thing. And finally, let's suppose that we were given the confidence interval values, but then required to work backwards to find the value of the sample proportion and the margin of error. This particular confidence interval stretches from 0.62 to 0.74. And we know that the value of p hat is going to be in the center of that confidence interval, and that the value of the margin of error would be the distance that's added between p hat and the right endpoint, or the distance from p hat and the left endpoint. To find the value of p hat, we need to find the midpoint between 0.62 and 0.74. So p hat is equal to 0.62 plus 0.74 divided by 2, which is 0.68. And the margin of error is the distance from the right endpoint, 0.74, down to the value of p hat, 0.68, which is a difference of 0.06. That can also be found by subtracting p hat, 0.68, minus the left endpoint, 0.62, and we also find 0.06.